Hi, welcome back to Narcolepsy Pumpkin. I'm Andy, and this week we're going to be looking at something a little more retro, but with a twist on software development. If you remember, a couple of episodes ago I suggested that looking at how old 8-bit architecture and hardware actually worked would potentially help you write better code even today. So I want to take a look at specifically the 6502, the microprocessor released by MOS in the 1970s. That processor is at the heart of most of the early 80s home computing scene, including the BBC Micro, the Electron. If you're in the UK, you'll remember those two. The Commodore 64 had a version of the 6502, which was the 6510. The original Nintendo Entertainment System also used a 6502. And most of the Atari machines, including the 400 and 800. It was also used in one of the iconic first home computers by a big tech company. Yes, the Apple I and Apple IIs, for that matter, used a 6502 processor. And the other advantage is they still make them today. Not exactly the MOS 6502, but there are 6502 processors you can buy today. Even in a chip shortage, you can have one of these delivered, and that makes it an interesting prospect for tinkering about with. Now, because this is primarily a software development channel and we only dip into retro tech when I get bored at weekends, what we're actually going to do is look at how hard it would be to write an emulator for the 6502 processor. Can't be that hard, can it? It's only 8-bit. Now, I'm not looking to write the world's closest emulation of a 6502. So the first thing you're going to have to do if you want to emulate a 6502 is actually understand what a 6502 does and what its instruction set is. There are lots of information pages about the 6502 on the internet. Find one that works for you. I used this one. I found there was a few mistakes on it, but it got me there at the end. So as you can see, one of the things to call out is that there are several different addressing modes for each of the opcodes on the 6502. Not all opcodes have different addressing modes, and not all of the opcodes that have addressing modes use all of the addressing modes. There are a set of instructions, and each of these we've got details of the addressing modes that uses. So if we go back here to these addressing modes, it's assuming that what you're talking about is the accumulator. Now you're probably thinking, what's an accumulator? The accumulator is one of 3 registers on the 6502 that you can use to put data in. You've got an accumulator, which tends to be the one that's used for any mathematical operations, any bitwise logic operations, and we've got X and Y, which tend to be used for indexes, but we can put a byte in and get a byte out of them. We can also transfer between the registers to a point. Also in the list of registers we have a program counter. That is literally the CPU's bookmark to where it's running code in memory. That is the only 16-bit register that exists on this processor, and it's 16-bit because it's a memory address. If we only had an 8-bit memory address, we'd only actually be able to address 256 bytes of RAM, which you wouldn't get a lot in. So we're using a 16-bit register, which allows us to address 64K of RAM. The 6502 uses mapped addressing for hardware access, so everything is a memory address. It doesn't matter whether it's actually memory, whether it's ROM, RAM, or a piece of hardware that it's talking to. It uses the same address bus and the same data bus to communicate. We've also got the status register, which is listed out here, where we've got a kind of internal state. These are all just bit flags that tell us whether the result of the last action was negative, overflowing, instigated decimal mode. Now, something to call out here, I didn't actually implement decimal mode because not very many things use it. The decimal mode on the 6502 means that it outputs the numbers as binary coded decimal when doing mathematics. So you're doing functions to add and take away. It puts the outputs as binary coded decimal, which really isn't used that much today. We've got interrupt. IRQ disable. 0 is literally that the value was 0, and carry is the carry flag. If you don't understand these, there again are a bit more information about it down here, and there's plenty of other sites that go into a bit more detail on how 6502 works and what all these flags do. The last register is the stack pointer, again 8-bit. It does point to a memory address, and that memory address is 16-bit, but it only has a single page. We've got what's called zero-page memory, which is easy to access single cycle because the page address is 00. So that's 00 and then 00 to FF is your first page of RAM. That's 0 page. The second page of RAM, 01, 00 and then to 0FF, 01FF, is actually used for your stack pointer. So those are the only kind of hard-coded bits of RAM that are used. There are some locations that it uses for vectors. So one of the other things you need to understand about a 6502 is what happens when you turn it on. So basically, when a 6502 starts, I think it's 7 cycle it runs, and then it actually looks at a memory location, and this is a hard-coded memory location, so this has to have an address for where you want it to jump to. Yeah, so there we go. We've got the reset vector. Address FFFC, 2 bytes in memory. So don't forget it was 16-bit memory addressing, so to hold a 16-bit address in memory we need 2 16-bit memory address locations. So we're looking at first high and low byte of the memory address. This holds a pointer to another memory address, which is where it will start executing. So that's what's going to set that program counter on that CPU's bookmark 2 when it sets off going, and from then on it starts running code. In order to implement a 6502, the sensible thing to do is start with kind of an easy-ish. So we'll have LDA is probably the easiest one to do, and that is loading the accumulator with something. That can be immediate, which is literally loading the next byte at the program counter into the accumulator. 0 page means that the next byte is a single byte, but that references an element of 0 page memory. So that'd be 00 and then whatever that byte is. 0 page X, which is X indexed, so useful when you're iterating over things, so you can keep incrementing X, decrementing X to move up and down as a pointer. 1 byte in total, which gives you the starting point in 0 page memory, and then whatever value is in the X register at that time is added to it. So if it's 0, it's just a straight 0 page. So where X is 0, the 0 page and 0 page X index will actually result in the same thing if they're given the same operand. Absolute is simply 2 bytes after that operand that actually give it the 16-bit memory address location to go and get the data from. Absolute Y, same thing, but is indexed by Y, so we're moving it, so we're going to that location, but that location plus whatever's in the Y. So again, useful if you're iterating over something in memory. But let's chip into what is going to be a hopefully short journey into how I approached this and what the outcome was, and then we can have a look at that running some actual code. Okay, so we switched across to an early commit in the journey. So you'll see here I've got a few unit tests in here. The one we need to actually look at is LDA. This isn't exactly where we started, this is where I ended up with the tests. So the first test to do, I think the first test I actually did right, was basically to create a dead machine. So something that started up and did nothing. I defined that I wanted it to, in that case where it had no code, vectors are all set to 0, that it just went to right to the end of memory. That's not what a 6502 does. There'll never be a case where this would ever really be hit, but it was just defining what I wanted the degenerate behavior to be. So this run to end bit, which again this came out, so this isn't something I went off and wrote initially, this is what was derived out of writing the tests and writing the code. So what I've ended up with is this empty 6502 state, and then I'm running around that, and this is just a functional loop, so we're just getting a new state based on the state and running a cycle. So that's pushing the processor a step through. So that meant I was able to effectively write very simplistic machine code. It's machine code, not assembler, so this is raw machine code, even though it looks a bit assemblery because I've got these nice names for the opcodes. So in opcode I've actually gone through and defined what all the opcodes are. Kill is actually a non-standard opcode. It's just one that's widely accepted, that if you actually pass 2 to it, the processor actually halts dead, and that genuinely happens on a real 6502. I thought that was a nice way to just detect the end of my bit of code I want to run, rather than having to do sort of permanent loops and things like that to detect, which is the usual way you'd do it if you were actually debugging assembler. You'd have something that actually branched and went back to itself, and in fact once we get a bit further down this journey you'll see that that is one of the ways I pinched a piece of machine code from somebody else who'd actually written all the tests you could ever do for every single function on a 6502, and that really did help with debugging, but we're not quite there yet. So the ones we're going to test are LDA. You can see that during this, at this point, I'd actually managed to test LDA, immediate, 0 page and 0 page X, but I've not tested all the other addressing modes. So back to test for LDA, what I'm doing is saying I'm using LDA immediate, and then I'm loading LDA with FE, so that's the first of my test. I'm doing ADC01, which is actually adding to the accumulator 1, which means that ends up being FF. So that takes the value in the accumulator, which is loaded with FE, add 1 to it, which comes out as FF, so that's put back into the accumulator. We're storing the accumulator in 0 page at 10, so that goes to 0010 as the 16-bit address space. We're loading the accumulator from 0 page, 0010, so we're just loading the value we've just stored straight back into, and that's the end of the code. And we're asserting that A equals FF, and that what's in the accumulator is negative. Now you're probably thinking, how do we know it's negative? Because it's just a byte. We're assuming based on 2's complement. Again, if you don't know what 2's complement is, go have a look at my blog. It actually explains it there. That's cleancraftsman.com. So if you have a look back at the opcode for load A, you can see here it has some little things where it's telling you what it should do with the registers. So again, it's showing me that the result should go back into A. Loading it in ends up in A, so it's memory to A. If that value is 0, we're going to set the 0 flag, and if it's negative, we're going to set the negative flag. Because it's FF, it is actually negative. Absolute guarantee that's negative. Because anything with the 7th bit set, that is going from bit 0 to bit 7, so the 7th bit, the higher bit is set, means that that number is negative. So it's a relatively easy test to do. With a bit of luck, actually run that test. And even this in early state, I'm pretty sure that will pass. Now, how is that implemented? Well, this is a little bit down the road, and in hindsight, I really should have done more commits. So that's me not doing what I preach and not committing things soon enough. So this just started off as a hobby, and then I decided I was going to do a video after I'd actually done it, so I was just giving it a go. What we've ended up with is CPU functions. This has a switch statement in it here, so we've got process LDA. If we go and look at that, we're using Shadow Quack, as well, seeing as it's my library, I tend to use it quite a lot. So we're going and getting the address out of memory, so we're passing in the memory here. Now that memory is being resolved here. So a bit of code that's going off and resolving that memory. So we're reading, working out whether it's immediate, absolute, indirect, whatever. And what we're basically saying here is that byte, we write that back to A. So we're creating a new state for the processor. We're writing the result, or the byte we've just loaded in from the memory address, into A. If B is 0, we'll set the 0 flag, and if it's negative, and all this is negative function does is actually check that the 7th bit is set, 128 being the 7th bit. Hopefully that makes sense. So that's, you know, how I've generally approached it and how I've ended up. Now you're probably wondering about the addressing. Now how I did that was I've got a few interfaces here. So I've got iAddress space, and the idea of that is that you've just got something you can read and write, and it's an interface for doing memory, and the implementation of address space. I decided to use a dictionary as kind of a map of memory, and we're simply using a U short, which is a unsigned short, which is actually just a 2-byte word that assumes it's unsigned. Nice and easy. Maps nice and easy to the memory addresses because it's a 16-bit value, and the values we pull out are a byte, and it's just the logic that pretty much just puts stuff in the memory or reads it out. If there isn't anything in the memory, or it's not stored anything in the dictionary already, just assumes it's 0. And at this point I was just about trying to work on my overlay, which was a way of delegating out bits of memory. So a way of having a delegate over the top, so overlaying something over the top of that address space, which was my intent of how to implement, you know, other bits of hardware or other functionality, things that do things slightly different to a straight read in, read out of memory. And you'll see that in the final thing. So what I'll do now is skip to the current state. So this is kind of where I started. So I'll skip to the current state, and you can see what I ended up with after doing this. So now we're looking at this in a almost current state. So this is before I decided to tinker with some stuff, but you'll notice here that there's the tests are now nicely separated from the abstractions, and runtimes all separate, a little bit better laid out. So what we've got is a 6502 state, and that is simply the program counter and the stack register and booleans for all the flags, and then the X, Y and A, didn't mean to do that, and the X accumulator and Y registers, each as bytes. So fairly simple layout, has no more knowledge of anything else at all. Got iAddress space, which has the placeholders for functionality, so we can set a reset vector, set an IRQ vector, we can get a reset vector, get IRQ vector, write at, which is a function to write a byte array out into starting at a memory address, write at writing a single byte at a memory address, and then read from a memory address a number of bytes into a byte array, and register overlay, which allows us to, as mentioned previously, an overlay, which is I overlay, that just has a start and end and a read and write. So it's a way of mapping other things other than straight memory onto the same memory address space. Seems to work. We've got a full list of opcodes, and you'll now see that quite a lot of these are referenced. In fact, I think pretty much all of them are. And we've got process kill exception, which is simply what happens if we go to the 6502 CPU, which is now called. So this has changed to a switch expression. You'll see that kill, there we go, causes that processor exception. What I have done is built something that's not cycle accurate, and by that I mean particular functions inside a processor take more than one cycle. what I've actually done is made an emulation that is one instruction per cycle, kind of. This means it will run 6502 byte code. So we should in theory be able to make it emulate a 6502 machine. My first thoughts on that was go back to my roots of the good old BBC Micro, like the one that sat behind me, because I have some knowledge of that hardware. I understand how it actually works. What I vastly underestimated was how hard it would be to emulate all the specialist chips that it requires to get a boot up sequence as part of its OS ROM to actually run inside my emulation. Now, I'm not saying that's impossible, and I probably would be able to get there eventually, but in terms of getting this video out, I decided to scale back my ambition considerably and go for something that was a much simpler set of hardware, a little more iconic, and that at least I could prove worked and had some basic support. So I went for the Apple I. Run unit tests over the top of that, and we'll see. So these tests run really quickly, took no time at all, and those are testing all the individual implementations of the operations. Now these run code tests, you notice here we've got a test Apple I, and yes, that is actually emulating an Apple I, so I did manage to do that. We'll come back to in a second. And this debug function, as aforementioned, so this actually uses a piece of assembler written by somebody else, not myself, which is a very intriguing set of tests that test, or supposedly test, every single function of the 6502 processor. And anytime it finds an error, it sticks itself in a loop. And all I've added here is a loop detection, which ends the run. And we're asserting that we actually get to the right place. So we get to the end of the tests, otherwise it ends early. We're also, and this is really bad practice because it's hard coded to a particular thing on my disk, to de-examples, it writes out a log and a dump. So that enables me, when this test was failing, I was having some issues debugging the processor, I was able to have a look at every single instruction it had run and a dump of the entire memory space as it stood. So that's just a very simple write out all the memory to a big 64K file. You'll notice from the code that this really represents a mashing together of both a functional and an object-oriented paradigm. And that goes to show that the two are not mutually exclusive. You can absolutely have something that's at the core functional and use interfaces to allow you to overlay and have abstraction and decoupling of code. That works really well. And it also allows you to pick and choose which fits the particular element of your program correctly. Some things may make more sense to be functional. Some things may make more sense to be a more object-oriented style, where you're having, a state that you can mutate. And that's one of the things I quite like about C#. It genuinely lends itself quite well to switching between paradigms and gives the choice back to the developer. Rather than going for a purely functional language or a purely object-oriented one, you got the best of both worlds. And there we go. So this should have an early version of what ended up being an Apple I emulator. Look a bit better. So there we go. We've got the slash. We don't have a flashing at sign, but I thought that was a bit too fancy. So we can ask it to look in bits of memory. So I'll ask it to look in F00, and it'll tell me there's nothing in there, which is what I kind of expected. So if I look in E000, which is actually the start of the basic ROM, we've got 4C in there. We can then do dot E0CO. That gives me all that memory. So this is the WAS monitor. So this is the OS that came with an Apple I. If I do E000R, that will put us into basic. So we're basically just moving the execution pointer at that point, and it started running basic. can now do the old print hello, and that should print hello. I can do line 10. Print hello. Line 20, go to 10. Everybody's done this. There we go. So that's running an emulation using my 6502 processor that I've written in C# and running an Apple One over the top of it. I had to implement some bits of the hardware to get the input and output up, but it's working. I later then decided to slightly extend that, so if I switch to my enhanced Apple One, and do build, so this should pick everything up and run that. So this has a bit more code built in. So first thing is, if I do D013, which is the register for the screen, and reset that with a 1, everything's now in green screen. I can also push to D014 and do 8, and then everything's now in grey. So we can reset D013 to 0, and we should have everything now white again. I'll do it in green screen. I've also loaded another ROM, which is the 30th birthday Apple One, which should be at 2080. Run. No, it's not. 0280. There we go. A lovely picture of Woz. Nice picture of Steve Jobs. The Apple logo. If you squint a bit, you can see that as Stephen was holding the Apple One. A picture of an Apple II. Picture of the Macintosh. An iMac. An iPod. And the MacBook Pro. And the next 30 years, the black Apple logo. And we'll loop round again. So that just to prove I've managed to build with that an Apple One. How I went about that. So all we've got is loading 3 ROMs in, so the Apple ROM, Basic ROM, and the Apple 30 code. That's loading it into, so FF00 for the Apple ROM, E000, which you saw me run, and at 0280 for the Apple 30. And then all we're doing is doing overlays for an Apple screen and Apple keyboard. Apple keyboard, just when it attempts to read from it, it's looking for particular addresses to what happens. So it's got a, are you ready for another character? Well, if there's a key available, then yes, FF returned. And then when it's trying to read, if there is a key available, it goes, gets the key and returns. So there's a bit of ASCII filtering about, but it basically just returns the byte ASCII to it. Setting bit 1, this is the interesting thing I found about the Apple One, is that for whatever reason, from the keyboard input and screen output, that the 7th bit is always pulled high. ASCII is only 7-bit, so it's not a problem, so we're just setting it, and that makes all the code work. Had some strange behaviour early on when I didn't realise that. Then the Apple screen is a simple output, and this is my extended Apple screen. So I've added, normally there's only from D12, D13, the only 2 that are actually hardware in the Apple One. Now I've just added a way of basically changing the foreground and background colour. And I've also forced it to, if the cursor gets beyond 40, we just roll over to the next line tidily. That's it. That's all the code that was needed. So, as a result of this project, I have actually got my own Apple One emulator that I wrote. And it works.
I can run software on it. My aim for this video is I'll inspire you to go and do the same thing. Rather than using my emulator, go and write your own. Approach it in the same way and you should come out with an emulator that works. All in all, end to end, it probably took me about a week's worth of work to write the emulator, and that's only spending maybe a couple of hours a night looking at it. And having to pick it up and put it down, again, probably extended the amount of time it took me to do it. And also, it was kind of a labour of love as opposed to something that I had a deadline for. That said, there's still some refactoring that could be done to the code as it stands today. I still want to actually sort some of the tests out, and I probably will do that, because my next challenge to myself is, well, I've done an Apple I. Next logical step would be see if I can emulate an Apple II. And these are computers I've never owned, so it gives me actually an insight into the hardware and how they were designed, because I'm having to emulate that. For the Apple I, the emulation, I've managed to do that just using the console keyboard input and the console output to the screen. Well, I hope you've enjoyed the video, I hope you've enjoyed the journey, and if you did, why not click on like and subscribe and click on the bell to get notifications when I post new videos. As always, thanks for watching.